What if everything you think you know about the beginning of the universe is only half the story? Picture this: an explosion of energy so unimaginably powerful that it set the stage for every galaxy, every star, and even the atoms in your body. The Big Bang is often treated like the ultimate answer, the grand finale of cosmic origins, but hidden in its afterglow are secrets most of us have never heard, clues that rewrite the rules of reality itself. For instance, did you know there's a cosmic fingerprint lingering in the void, a whisper from the universe's first trillionth of a second? Or that the very fabric of space might be stitched together by forces science is only beginning to understand? These aren't just abstract ideas, they're pieces of a puzzle that could redefine how we see existence. And yet, so many of these mind-bending truths get overshadowed by the same handful of facts repeated in documentaries and textbooks. That's why today we're diving deep into 25 forgotten revelations about how it all began. From phantom dimensions lurking beyond our perception to the shocking role chaos played in shaping the cosmos, each of these facts will make you question what you thought was possible. This isn't just a history lesson, it's a journey to the edge of human understanding, where the universe's most guarded secrets start to unravel, so buckle up. By the time we're done, you'll never look at the night sky the same way again. We've all been taught the universe is roughly 13.8 billion years old, a number etched into textbooks like cosmic gospel. But what if that's just the prologue to a much longer story? Recent discoveries are turning that tidy timeline upside down, starting with quasars, those brilliant, ancient beacons lurking at the edge of observable space. Some of these cosmic lighthouses appear older than the universe itself, shining with a maturity that defies explanation. Take the quasar J134 plus 0926, for example. Its light suggests it formed when the cosmos was a mere 670 million years old, yet it's as massive as 10 billion suns. Building something that colossal so quickly is like finding a skyscraper in the ruins of a Stone Age village. It shouldn't exist under our current models. Even stranger, certain galaxies exhibit redshift anomalies, their light stretched in ways that don't align with the expected expansion of space. One provocative theory suggests these inconsistencies vanish if we rewind the clock further, doubling the universe's age to 26.7 billion years. This isn't just a tweak to the numbers, it's a direct challenge to the lambda CDM model, the backbone of modern cosmology. That framework relies on dark energy and cold dark matter to explain how the universe evolved. But if the cosmos is nearly twice as old, suddenly dark energy's role shrinks, and the mysterious push behind cosmic acceleration might not be so dominant after all. Critics argue these anomalies could stem from measurement errors or unknown physics rather than rewriting time itself. But if the evidence holds, we're staring at a cosmic paradigm shift, one where the Big Bang wasn't the absolute beginning, but a rebirth from something even older. Imagine peeling back the layers of space-time only to find another universe's echoes beneath. If the universe truly is older than we thought, one of the biggest puzzles it solves is the baffling maturity of those early galaxies, how they grew so massive, so fast. But this revelation doesn't just tidy up cosmic history, it rips open a new paradox, one that challenges the very laws of thermodynamics. Energy can't be created or destroyed, yet the early universe seems to have defied that rule, assembling giant structures with a speed that should have taken billions of extra years. If we stretch the timeline, suddenly those ancient galaxies have the breathing room they need to form naturally. But here's the twist: dark energy's influence shrinks in this older universe, and that throws a wrench into our understanding of cosmic inflation. Think of it like blowing up a balloon. The standard model says dark energy kicked in around 5 billion years ago, causing space to expand faster and faster. But if the universe is nearly twice as old, that acceleration becomes a minor footnote in a much longer story. The numbers just don't add up the way they used to. Some theorists suggest dark energy might not be a constant force after all, that it could fluctuate, fade, or even reverse over eons. Others propose gravity itself behaves differently on cosmic timescales, subtly warping the rules we thought were set in stone. Then there's the eerie silence of the cosmic microwave background, the afterglow of the Big Bang. Its temperature fluctuations are too smooth, too uniform for a universe that supposedly roared into existence in a split second. An older cosmos might explain that too, giving space more time to even out. But that just leads us to another cliffhanger. What filled those extra billions of years? Was there a slower, colder birth before the fireworks began? The more we tug on these threads, the clearer it becomes the universe's origin story is far from written. It's a living mystery, and every answer we uncover only deepens the enigma. What if the answer to dark matter has been hiding in plain sight since the first moments after the Big Bang? Not exotic particles or undiscovered forces, but tiny, ancient black holes, so small they could fit in your hand, yet so dense they outweigh mountains. These hypothetical objects, known as primordial black holes, might have formed when the newborn universe was less than a second old, in regions where space-time itself crumpled under extreme density. Unlike the black holes we know today, born from collapsing stars, these relics would be remnants of cosmic chaos forged in the furnace of creation. Stephen Hawking first proposed their existence back in 1971, calculating that such black holes could range from microscopic to asteroid size. Here's the startling part: if enough of them survived, they could account for the invisible mass we call dark matter. That's right, the very fabric of the cosmos might be threaded with countless invisible holes, each a fossil from the universe's first breath. While most black holes evaporate over eons due to Hawking radiation, the largest primordial ones could still linger, lurking unseen in the voids between galaxies. Recent gravitational wave detections have added fuel to this theory. When observatories like LIGO catch ripples in space-time from colliding black holes, some of these events involve objects too light to fit conventional star collapse models. Could these be primordial black holes dancing in the dark? Even more tantalizing are the unexplained microlensing events, brief flashes of light when something massive but invisible bends starlight. These cosmic ghosts match predictions for how primordial black holes would behave. Of course, skeptics point out gaps. If these objects were everywhere, why haven't we seen more direct evidence? Some models suggest they disrupt neutron stars or distort the cosmic microwave background in ways we haven't observed. But proponents argue we might simply be looking for them wrong, like searching for a shadow in a pitch-black room. Future telescopes hunting for gravitational waves or quantum signatures could settle the debate. Imagine the implications. If dark matter turns out to be a swarm of ancient black holes, it would rewrite not just cosmology but the story of our universe's infancy. Suddenly, the mysterious weight holding galaxies together isn't an unknown particle, it's a hidden graveyard of primordial titans, each a silent witness to the first tick of the cosmic clock. The hunt for these ghosts is more than scientific curiosity, it's a quest to touch the remnants of creation itself. But what if our universe isn't alone? What if there's a phantom twin, a mirror reality where time flows backward and atoms are built from antimatter? This isn't science fiction, it's a serious theory rooted in the laws of physics. According to CPT symmetry, one of the most fundamental principles in quantum mechanics, every particle in existence should have an inverted counterpart, same mass, opposite charge, and reversed in time. Apply that to the Big Bang, and you get a mind-bending possibility, a second universe, born in the same instant as ours but ticking in reverse. The evidence for this cosmic doppelganger lies in the subtle wrinkles of the cosmic microwave background. Those faint temperature variations, the echoes of the universe's birth, show peculiar asymmetries, regions where matter clumps differently than expected. Some physicists argue these anomalies could be gravitational footprints from our antimatter twin, tugging at the fabric of space from the other side of creation. Even neutrinos, those ghostly particles that barely interact with matter, hint at this duality. They oscillate in ways that suggest time might not be the one-way street we assume. Here's where it gets stranger. In this mirrored universe, causality would flip. A cup shattering on the floor here might, from their perspective, spontaneously reassemble on a table. Stars wouldn't burn, they'd unburn, drawing light back into themselves. But before you imagine crossing over, remember, the boundary between these realities would be the Big Bang itself, a wall of infinite energy. We'd never meet our counterparts, yet their existence could solve one of cosmology's biggest mysteries. Why matter dominates our universe when the Big Bang should have created equal parts matter and antimatter? Critics counter that CPT symmetry doesn't require a twin universe, just that the math allows it. And so far, no telescope has spotted definitive proof of antimatter galaxies or reverse time supernova. But if future experiments like precision measurements of the CMB or neutrino behavior find even a whisper of this phantom twin, it would rewrite not just our cosmic history but the nature of reality itself. Suddenly, the Big Bang isn't a beginning, it's a collision of two timelines, forever entangled yet forever apart. The cosmos isn't just vast, it's eerily empty. For decades, scientists have grappled with Fermi's paradox. If the universe is teeming with potential for life, why haven't we heard a single whisper from another civilization? One chilling answer lies in the early filter hypothesis, a cosmic gauntlet so deadly that 99% of civilizations might perish before they even glimpse the stars. The universe, it seems, isn't just indifferent to life, it might be actively hostile. Take gamma-ray bursts, for example. These are the universe's most violent explosions, capable of sterilizing entire galaxies in seconds. When a massive star collapses or neutron stars collide, they unleash beams of energy so intense they can strip atmospheres clean off planets light years away. Earth has dodged this bullet so far, but the early universe was a shooting gallery. During cosmic dawn, those chaotic first billion years, gamma-ray bursts were 1,000 times more frequent. Any fledgling civilization rising in that era would face near certain annihilation, their potential snuffed out before they could even invent radio. Then there's vacuum decay, a theoretical doomsday hiding in the fabric of reality itself. Quantum fields that govern the universe might not be in their most stable state. If a single pocket of space-time tipped over into a lower energy state, it could trigger a cascading phase change, rewriting the laws of physics at light speed. Entire regions of the universe could vanish in an instant, erased so thoroughly that not even light would escape. The terrifying part, this could happen anywhere, anytime, with no warning. If life is rare, it might be because the universe is fundamentally unstable, a house of cards waiting to collapse. But here's the twist, the silence might actually be good news. If the filter is behind us, if humanity has already survived the universe's deadliest trials, we could be among the first generation of civilizations to reach the cosmic stage. Alternatively, if the filter still lies ahead, every quiet star system is a grim omen, a signpost warning of horrors we haven't yet faced. The great silence isn't just a mystery, it's a countdown and the clock is ticking. Space isn't just empty, it's alive with quantum chaos, a seething ocean of virtual particles flickering in and out of existence so fast we can't see them. But what if this microscopic frenzy left scars on the cosmos? Enter quantum foam, a dizzying concept where space-time itself bubbles like boiling water at scales 1 billion trillion times smaller than an atom. According to theory, these fleeting fluctuations might have frozen into the fabric of the universe during its fiery birth, leaving behind primordial ripples we could still detect today. Pulsars, the universe's most precise clocks, hold the key to finding these fossils. These spinning neutron stars beam out radio waves with such regularity that a deviation of 1 millisecond over centuries would be like a clock losing a single second in 30 million years. Yet some pulsars do hiccup unpredictably, and scientists suspect quantum foam could be the culprit. Imagine space-time as an old vinyl record. At macro scales, it looks smooth, but zoom in close enough and you'll find scratches, tiny warps that distort the music. Quantum foam would do the same to pulsar signals, stretching and squeezing them as they travel through this frothy subatomic terrain, the telltale sign. A specific type of noise in pulsar timing arrays networks of these cosmic metronomes monitored across galaxies. If the foam exists, their collective ticks should reveal a faint statistical jitter, a fingerprint of spacetime's grainy origins. Projects like NANOGRAV are already hunting for this signal, sifting through decades of pulsar data for patterns that defy conventional physics. But here's the twist: if we find it, we might be staring at evidence of a universe before the Big Bang. Some models suggest quantum foam could be remnants of a prior cosmic cycle, like bubbles in a sinkhole draining into another dimension. Others argue it's proof of hidden extra dimensions curling in on themselves, their vibrations imprinting on our reality. Skeptics counter that pulsar anomalies could stem from interstellar gas or magnetic fields, yet the hunt continues because the payoff would rewrite physics. Detecting quantum foam wouldn't just solve a mystery, it would bridge the gap between Einstein's relativity and quantum mechanics, two theories that refuse to coexist. Suddenly, the void between stars isn't just empty, it's a buzzing archive of creation's first moments, whispering secrets in the static between pulsar beats. And if we learn to listen, we might finally hear the universe's oldest song. The universe is hiding something literally. When scientists calculated how much lithium should exist based on Big Bang nucleosynthesis, that crucial 3-minute window when hydrogen fused into the first elements, the numbers came up shockingly short. Theory predicted the cosmos should hold 3 times more lithium-7 than we've actually detected. This isn't just a rounding error, it's a gaping hole in our understanding of creation's chemistry lab. So where did the missing lithium go? One radical idea points to supersymmetric particles, hypothetical heavy cousins of known particles that might have existed in the early universe's extreme conditions. If these exotic entities formed and then decayed, they could have gobbled up lithium nuclei like cosmic Pac-Men, converting them into other elements before the universe cooled. Particle accelerators like the Large Hadron Collider are hunting for traces of these phantom particles, hoping to catch them in fleeting collisions. But there's a twist. Some astronomers argue the lithium never vanished, it just moved. Stars like red giants act as elemental factories, burning lighter elements in their cores. Over billions of years, they might have processed primordial lithium into heavier elements, effectively hiding it in plain sight. Others propose that cosmic rays, high-energy particles racing through space, could have shattered lithium atoms in interstellar gas, like bullets smashing fragile glass sculptures. The most mind-bending solution: lithium might have never existed at predicted levels to begin with. If the early universe's density or temperature fluctuated in ways we haven't accounted for, our nucleosynthesis models could be fundamentally flawed. Imagine baking a cake where the recipe insists you'll get 12 slices, but the oven's quirks mean only 4 actually form. This isn't just about lithium, it's a litmus test for the Big Bang itself. If exotic physics or hidden stellar processes can rewrite elemental abundances, what else have we miscalculated about the universe's first moments? Every undetected atom whispers that our cosmic origin story might need another draft. The cosmic microwave background should be a random snapshot of the universe's infancy, a hazy glow with temperature variations scattered like paint splatters on a canvas. But when scientists mapped it, they stumbled onto something unsettling. The hot and cold spots aren't as chaotic as they should be. Instead, they align eerily with the plane of our solar system, forming a pattern so improbable that researchers dubbed it the axis of evil. This isn't just a quirky name. It's a full-blown crisis for cosmology because it hints that either the universe has a built-in preferred direction, something the Big Bang vehemently denies, or our entire understanding of the CMB is somehow tainted by an unseen bias. Picture throwing darts blindfolded and hitting bullseyes in a perfect line. That's the statistical absurdity we're dealing with. The odds of this alignment happening by chance are less than 1 in 1,000, yet there it is, etched into the oldest light we can observe. One explanation is contamination. Our solar system's motion through space might be distorting the CMB's signal, like wind smearing raindrops on a car window. But even after correcting for this so-called kinematic dipole, the anomaly persists stubborn as a fingerprint on a crime scene. Then there's the radical alternative. What if the universe does have a preferred axis? Some theorists suggest this alignment could be a relic from before the Big Bang, a cosmic bruise left by an earlier phase of existence. Imagine two universes colliding in a higher dimensional space, their impact imprinting a directional twist on our newborn cosmos. Others propose that dark energy isn't uniform but flows along invisible cosmic strings, warping the universe's expansion like tides tugging at the shore. But the most unsettling possibility, that we're seeing evidence of a multiverse. If our universe is one bubble among countless others, its birth might have been nudged by neighboring realities, leaving behind asymmetries we're only now detecting. Skeptics argue the axis of evil could vanish with better data after all. The Planck satellite's measurements are still humanity's best grainy Polaroid of the early universe. Future observatories like the upcoming CMB Stage 4 project aim to scan the sky with 10 times the precision, potentially resolving the mystery once and for all. For now, the axis of evil remains a cosmic riddle wrapped in a paradox. If it's real, it undermines the foundational principle that the universe has no center, no special direction. And if it's an illusion, we're left wondering what else we might be misreading in the faint afterglow of creation. Either way, it's a reminder that the universe's first whisper still holds secrets we've barely begun to decode. The universe has a strange prejudice, one so fundamental that without it, you wouldn't exist. For every billion particles of antimatter created in the Big Bang, there were 1,000,001 particles of matter. That tiny surplus, known as baryon asymmetry, is the sole reason anything solid persists in the cosmos. But why the imbalance? The answer might lie with the most aloof particles in existence, neutrinos and their hypothetical dark siblings that vanished in the universe's first microsecond. Neutrinos are cosmic ghosts zipping through planets like they're not even there. But what if these particles are also their own antimatter opposites? This bizarre quality, called the Majorana nature, would mean a neutrino could literally annihilate itself, a property no other known particle shares. If true, it would explain how the early universe tipped the scales. Here's how. In the seething plasma of the first second, heavy right-handed neutrinos, theorized partners to the ones we've detected, may have decayed unevenly, spitting out slightly more matter than antimatter. Each decay would have been a microscopic nudge, but across the entire cosmos, those nudges piled up into the overwhelming matter dominance we see today. The math behind this, called the seesaw mechanism, is elegant. Imagine a playground seesaw with an invisible child on one end. The heavier the hypothetical right-handed neutrino, the lighter our familiar left-handed ones become. These ultra-heavy ghosts would have been fleeting, vanishing almost instantly after the Big Bang, but their decay could have seeded the universe with just enough matter to forge galaxies. Experiments like neutrinoless double beta decay searches are hunting for proof. If certain unstable atomic nuclei decay without emitting neutrinos, a smoking gun for Majorana particles, it would confirm neutrinos are their own antimatter twins. Meanwhile, particle colliders are probing energy regimes where right-handed neutrinos might briefly flicker into existence. Even cosmic inflation plays a role. If the universe expanded rapidly enough, it could have stretched those early decays into permanent cosmic imbalance. Critics point out gaps. No right-handed neutrinos have been spotted, and the seesaw mechanism remains unproven. But if either piece falls into place, we'll have cracked one of physics' deepest mysteries: why the universe favors existence over annihilation. The answer, it seems, was hiding in particles so elusive they barely interact with reality at all. Imagine a universe so young that stars hadn't yet flickered to life, a cosmic nursery where chemistry itself was taking its first tentative steps. In that primordial darkness, just 100,000 years after the Big Bang, the very first molecule emerged: helium hydride, a fragile pairing of helium and a hydrogen ion. For decades, this theoretical pioneer existed only in equations, a ghost from the universe's infancy that should have vanished without a trace. But in 2019, NASA Flying Observatory, SOFIA, did the impossible. It caught a whisper of helium hydride in a planetary nebula 3,000 light-years away, confirming a prediction nearly a century old. Why does this matter? Because helium hydride was the spark that ignited cosmic chemistry. Picture the early universe as a simmering broth of charged particles, so hot that atoms couldn't stabilize. As everything cooled, helium, the universe's second most abundant element, finally grabbed a lone hydrogen ion, forming a bond that let energy escape more efficiently. This single reaction was the universe's first chemical handshake, cooling the cosmic soup just enough for neutral hydrogen atoms to form. Without that tiny molecular stepping stone, the universe might have remained a featureless plasma forever, never giving rise to the rich tapestry of molecules that built galaxies and us. The catch: helium hydride is absurdly fragile. In modern space, it's shredded by ultraviolet light almost instantly. That's why SOFIA's discovery in NGC 7027, a nebula mimicking conditions of the early cosmos, was so groundbreaking. The telescope's infrared eyes spotted the molecule's faint fingerprint at a wavelength of 0.149 millimeters, a signal so precise it could only mean one thing: helium hydride wasn't just a theoretical footnote. It was real, and its survival in that nebula proved our models of cosmic dawn were correct. But here's the twist: helium hydride isn't just a relic, it's a cosmic sleuth. By studying where and how it forms, scientists can trace the conditions of the universe's first chemical reactions. Some theories suggest pockets of helium hydride might still linger in the deepest voids, untouched by starlight. Others propose it played a role in seeding the complexity that led to water and organic molecules. The hunt now turns to upcoming telescopes like the James Webb Space Telescope, which could detect helium hydride's faint glow in even older corners of space. If found, it would be like uncovering a fossilized footprint from the moment the universe learned to build. Not bad for a molecule so simple it barely lasts a heartbeat in today's cosmos. 22 billion years from now, the universe might die not with a whimper, but a scream. Meet phantom energy, a theoretical variant of dark energy so potent it could unravel reality itself. While regular dark energy pushes galaxies apart at an ever-increasing rate, its more sinister cousin would grow stronger over time, accelerating until it overcomes every force that holds the cosmos together. First predicted by physicist Robert Caldwell in 2003, this doomsday scenario called the Big Rip would start by shredding galaxy clusters, then stars, then planets, until finally, nanoseconds before the end, even atoms are torn apart by the unstoppable stretching of space itself. The evidence for this nightmare fuel comes from an unlikely source: exploding stars. Type Ia supernovas serve as cosmic mile markers because they all explode with nearly identical brightness. By measuring how dim they appear across vast distances, astronomers can track how fast the universe expands. But in the late 1990s, researchers noticed something bizarre: these stellar explosions were fainter than expected, meaning the universe wasn't just expanding, it was accelerating. That discovery earned a Nobel Prize and pointed to dark energy's existence. Yet newer data reveals a troubling twist. Some supernovas suggest the acceleration isn't constant but speeding up faster than our models predict. Enter phantom energy. If this exotic form of dark energy exists, its density would increase as space expands, unlike regular dark energy which stays constant. Picture a car whose gas pedal gets heavier the faster it goes eventually. The engine redlines and the vehicle tears itself apart. In cosmic terms, that moment arrives when phantom energy's repulsive force overwhelms gravity, electromagnetism, even the strong nuclear force binding atomic nuclei. Galaxies would first blink out of view as space stretches faster than light can cross it. Then, about 3 months before doomsday, the Milky Way would disintegrate. Earth would explode hours before the end, and in the final fractions of a second, space-time would stretch so violently that quarks, the building blocks of protons, would be ripped apart. Critics argue phantom energy violates energy conditions central to general relativity, calling it a mathematical curiosity rather than a physical reality. Others counter that quantum field theory allows for such exotic states, even if they seem unnatural. The key test lies in future supernova surveys. If astronomers find that distant explosions appear progressively dimmer than current acceleration predicts, it could signal phantom energy's presence. Projects like the Vera Rubin Observatory, set to map millions of supernova, may soon tip the scales. The chilling implication: if phantom energy exists, the countdown has already started. 22 billion years might sound like an eternity, but on cosmic scales, it's the blink of an eye. Worse yet, there'd be no warning when the end nears, just an inexorable slide into silence as the universe's fabric stretches too thin to hold itself together. The Big Rip isn't just a theory, it's a reminder that even the laws of physics might have an expiration date. The universe won't end with fire or ice, but with a slow, silent whisper, the last gasp of black holes dissolving into nothingness. We've all heard the dramatic theories: the Big Crunch, the Big Freeze, even the Big Rip, but none are as hauntingly inevitable as the black hole era. Imagine a cosmos so old that every star has burned out, every galaxy has faded to dust, and the only structures left are the universe's most voracious predators, now starving in the dark. These black holes, once rulers of gravity, will become the final flickering candles in an endless night. Their existence measured in Google's numbers so large they dwarf the age of our current universe by factors of trillions. Here's how it unfolds. After all stars exhaust their fuel, roughly 100 trillion years from now, the universe enters the degenerate era, a wasteland of cooling white dwarfs and dead neutron stars. But given enough time, even these remnants will decay. Quantum mechanics guarantees it. Protons, the very building blocks of matter, aren't immortal. Current models suggest they'll disintegrate over 10 to the power of 34 years, leaving behind a sea of loose particles too feeble to form atoms. Yet black holes persist, feasting on this subatomic debris until there's nothing left to consume. That's when Hawking radiation takes center stage. According to Stephen Hawking's groundbreaking work, black holes aren't truly black. They glow faintly, leaking energy particle by particle. The smaller the black hole, the faster it evaporates. Stellar mass black holes might vanish in 10 to the power of 67 years, but the supermassive ones anchoring galaxies, those could linger for 10 to the power of 100 years, a time span so vast it makes the current age of the universe seem like a single heartbeat. During this era, space becomes a graveyard of epic proportions. Isolated black holes drift through absolute darkness, their event horizons shrinking as they shed mass. The last ones standing will be monoliths of solitude, radiating their final energy in bursts of gamma rays before popping out of existence like soap bubbles. And then nothing, no light, no heat, no structure, just an endless expanse of photons too weak to interact, space so cold that temperature loses all meaning. But here's the chilling irony. Even this bleak future isn't the end. Some theories suggest quantum fluctuations might spark new big bangs in the emptiness, birthing fresh universes from the ashes of the old. Others propose that dark energy's grip could weaken, allowing gravity to claw back its dominance in a cosmic cycle of death and rebirth. For now, these ideas remain speculative, but they hint at a universe far stranger than we've dared to imagine. The black hole era isn't just a footnote in cosmic history, it's a reminder that even in oblivion, the universe writes its own rules. Before the first stars flickered to life, before atoms even took shape, the universe was flooded with an invisible tide, neutrinos streaming freely through space like ghosts passing through walls. These particles, born just 1 second after the Big Bang, carry secrets older than light itself. While the cosmic microwave background reveals the universe at 380,000 years old, the cosmic neutrino background, if we could detect it, would show us the cosmos in its first breath, a snapshot of creation still echoing across the void. Neutrinos are the ultimate escape artists. 1 trillion pass through your body every second without a trace, barely interacting with matter at all. That makes them perfect cosmic messengers, but also nearly impossible to catch. The relic neutrinos from the Big Bang are especially elusive. After racing across the universe for 13.8 billion years, they've slowed to a crawl, their energy diluted by the expansion of space until they're barely moving at all. Catching one would be like detecting a whisper in a hurricane, yet scientists are building traps for these phantoms. Projects like PTOLEM-Y at Princeton aim to capture neutrino fingerprints using sheets of graphene chilled to near absolute zero. When a relic neutrino, expected to carry just a fraction of the energy of a visible photon, strikes an atomic nucleus, it should produce a minuscule recoil, a wobble smaller than the width of an atom. Other experiments, like the proposed cryogenic underground observatory for rare events, hunt for neutrino interactions in vats of ultra-pure liquid argon buried deep underground, shielded from cosmic rays that could drown out the signal. Why go to such extremes? Because these neutrinos hold a map to the universe's first second. Unlike the cosmic microwave background, which shows us the universe after it cooled enough for atoms to form, the neutrino background would reveal the era when matter was still a seething plasma, so dense that even light couldn't escape. The patterns in these ghostly particles could expose hidden wrinkles in inflation, the mysterious process that stretched the infant universe from subatomic to cosmic scales in less than a blink. The challenge isn't just technical, it's theoretical. Standard models predict relic neutrinos should be everywhere, but their expected energy is so low that current detectors might never spot them. Some physicists speculate these particles could have interacted with dark matter, subtly shifting their properties over billions of years. Others suggest neutrinos from the Big Bang might have decayed into even stranger particles, leaving behind only faint traces for us to decipher. If we succeed, the payoff would rewrite cosmology. The cosmic neutrino background could reveal whether our universe had siblings, other domains born from the same inflationary event, or if dark energy was already shaping space-time in those earliest moments. It's a direct line to the dawn of time, a whisper waiting to be heard, and when we finally tune our instruments to the right frequency, the universe's oldest ghosts might finally tell their story. What if everything we perceive as reality, every galaxy, every atom, even the space between them, is nothing more than an elaborate illusion? The holographic principle, a radical idea born from black hole physics, suggests exactly that. It all started when physicist Jacob Bekenstein discovered something astonishing in the 1970s. The entropy, or information content, of a black hole isn't proportional to its volume but to its surface area. This realization turned our understanding of reality inside out. If a black hole's event horizon, a flat, two-dimensional boundary, can encode everything that falls into its three-dimensional depths, could our entire universe work the same way? Let's break this down. Imagine watching a movie in 3 dimensions. You see depth, texture, movement, but all that information is actually stored on a flat, 2-dimensional screen. The holographic principle proposes that the universe operates similarly. Every particle, every force, every tick of time might emerge from a hidden layer of information painted onto the cosmic horizon, the farthest reaches of observable space. This isn't just philosophy, it's math. String theorists like Leonard Susskind later showed how the equations could balance, with our 3D reality emerging from a 2D boundary like a hologram emerging from a laser-etched plate. Now tie this to the Big Bang. At the moment of singularity, the entire universe was compressed into an infinitely dense point, a state that defies physics as we know it. But if the holographic principle holds, that singularity wasn't a true 0-dimensional dot. Instead, it could have been a 2-dimensional surface unfurling into the 3-dimensional cosmos we inhabit today. Think of it like blowing up a balloon. The Big Bang didn't happen inside space. It created space by projecting information outward from a flat boundary. The implications are staggering. If the universe is a hologram, it would explain why quantum mechanics and gravity refuse to reconcile. They might be different languages describing the same underlying code. Even time could be an emergent property, a side effect of how information is processed at the cosmic scale. Experiments like the holometer at Fermilab have searched for telltale pixelation in spacetime, hints that reality has a finite resolution like a digital image. While results remain inconclusive, future gravitational wave detectors might spot anomalies in black hole mergers that betray the universe's holographic skeleton. Critics argue this is speculative, that without direct evidence it's just elegant math. But if proven, the holographic principle would rewrite not just cosmology but our place within it. Suddenly, the Big Bang isn't the beginning of matter and energy, it's the rendering of a cosmic simulation, a universe waking up from equations etched on the edge of nothingness. And if that's true, the real question isn't how our universe began, but who or what pressed play. The Boltzmann brain paradox is one of those ideas that starts as a fascinating thought experiment and ends up making you question whether anything you perceive is real. Picture this: given enough time, even in a cold, empty universe, random quantum fluctuations could spontaneously assemble a fully formed, self-aware brain. Not attached to a body, not born from evolution, but conjured from sheer chaos, complete with false memories of an entire life that never happened. According to thermodynamics, given infinite time, even the most improbable events become inevitable. So statistically, shouldn't the cosmos be teeming with these disembodied observers, each convinced they're real while the rest of reality is an illusion? This isn't just philosophical musing, it's a direct challenge to how we understand cosmology. If the universe truly is eternal or cyclic, Boltzmann brains should vastly outnumber ordinary minds like ours. After all, assembling a single conscious entity through random particle collisions is infinitely more probable than the gradual evolution of billions of organisms across billions of years. Yet we don't see evidence of these phantom minds, which implies something's fundamentally wrong with our assumptions. One escape route: the universe isn't eternal. If spacetime had a definitive beginning like the Big Bang, it hasn't existed long enough for Boltzmann brains to dominate. Inflation theory also offers a fix. If the early universe expanded exponentially fast, it could have locked in low entropy conditions, making structured, biological consciousness more likely than random fluctuations. But skeptics counter that even our observable universe might be a fluke, a temporary dip in entropy amid an ocean of chaos. The paradox cuts deeper when applied to quantum mechanics. In the many worlds interpretation, every possible outcome spawns a new reality. Given infinite branching, doesn't that guarantee a universe where Boltzmann brains emerge constantly? Some theorists spin this nightmare into a testable prediction. If we live in a high-entropy cosmos where such minds are inevitable, our observations should eventually reveal impossible anomalies, glitches in reality, like stars rearranging themselves overnight or physics constants shifting randomly. Of course, there's a haunting flip side. What if we're the Boltzmann brains? Modern simulations already create conscious seeming AI with fabricated memories. If advanced civilizations run ancestor simulations at scale, the number of simulated minds could dwarf biological ones. Combine that with quantum fluctuation odds, and the probability tilts unnervingly toward us being the random accidents, not the products of a 13.8 billion-year cosmic drama. The chilling beauty of this paradox is that it can't be entirely dismissed. It forces us to confront the fragility of our assumptions about time, entropy, and observation. Maybe the answer lies in a theory we haven't discovered yet, one that places hard limits on how reality can fluctuate. Or perhaps the paradox itself is a clue, whispering that the universe is far stranger, far more selective about allowing observers like us to exist. Either way, it's a reminder that even the laws of physics might have unspoken rules, boundaries we've yet to perceive. Eternal inflation theory doesn't just suggest our universe is expanding. It claims the cosmos is birthing new realities endlessly, like bubbles in a boiling pot of water. Imagine space itself stretching exponentially, not just here but everywhere, with quantum fluctuations sparking new big bangs in distant pockets. Each of these bubbles becomes its own universe, complete with unique physics. Some with gravity so weak that matter never clumps into galaxies, others where atoms can't even form because the nuclear forces are too strong. This isn't science fiction, it's a direct consequence of quantum mechanics meeting general relativity. In the 1980s, physicist Alan Guth proposed that inflation, the ultra-fast expansion of the early universe, might not have been a one-time event. Instead, it could be self-sustaining, driven by a peculiar energy field called the inflaton. Here's where it gets wild. While most of space stops inflating and cools into a stable universe like ours, other regions keep stretching forever, spawning new bubbles of reality ad infinitum. Picture a cosmic tree with infinite branches, each a self-contained universe governed by its own rules. Some of these realities might be barren, with constants so hostile that stars ignite and burn out in seconds. Others could be so stable that black holes never form, leaving galaxies to drift undisturbed for eternity. The truly unsettling part, this isn't just speculation, it's a framework that solves real cosmological puzzles. For example, why does our universe have such finely tuned constants that allow for life? In an infinite multiverse, statistically, some bubbles must hit the jackpot. We're not special, we're just the winners of a cosmic lottery. Critics argue this is untestable. How do you observe a universe separated from ours by an infinite expanse of inflating space? But counterintuitively, there might be fingerprints. If two bubble universes ever brushed against each other in the early cosmos, the collision could have left scars in the cosmic microwave background. Satellite data has even flagged odd features like the infamous cold spot as potential evidence of such an encounter. Future telescopes mapping the CMBWITH Chinese letter precision could settle the debate. The implications are staggering. If eternal inflation is real, time and space have no true beginning, just an endless fractal of creation where universes are born, live, and die without ever knowing they're part of something infinitely larger. Our Big Bang wasn't the start, it was just another bubble in an ocean of infinity. And somewhere out there, another version of you might be hearing this same story, in a universe where the laws of physics made it all possible. Before the first galaxies, before even the faintest whisper of heavy elements, the universe burned with stars unlike any we've ever seen. These weren't just ancient, they were primordial titans, blazing with such ferocity that they rewrote the rules of stellar physics. Meet population 3 stars, the universe's first nuclear furnaces, thought to have been 300 times more massive than our Sun, and so pure they contained nothing but hydrogen and helium. No carbon, no oxygen, not a single grain of dust, just the raw ingredients of creation itself. These behemoths were cosmic alchemists operating in a laboratory without tools. Under normal conditions, a star's lifespan is shaped by heavier elements that help it radiate away heat, slowing its collapse. But population 3 stars had no such breaks. Their pristine composition made them far hotter and denser than modern stars, burning through their fuel in mere millions of years before erupting in supernovas so violent they'd make today's stellar explosions look like firecrackers. The energy released in these deaths wasn't just light. It was the crucible that forged the universe's first heavy elements, scattering carbon, oxygen, and iron into the void where only hydrogen and helium had existed before. Here's where it gets even stranger. Unlike modern supernovas, which leave behind neutron stars or black holes, the death throes of these early giants might have been something far more exotic: pair instability supernovas. When a star's core reaches temperatures high enough to spontaneously create electron-positron pairs, the sudden loss of thermal pressure causes a catastrophic collapse followed by a runaway thermonuclear explosion. The entire star detonates, leaving no remnant behind, just pure, unfiltered energy converting starlight into the building blocks of future planets and life. The evidence for these vanished leviathans lies in the most metal-poor stars we've found. Ancient survivors like He 1057-224, lurking in the Milky Way's halo, contain trace amounts of elements that could only have been forged in the hearts of those first, unimaginably massive stars. Their chemical fingerprints are like cosmic archaeology, revealing a time when the universe was young enough to remember its own fiery birth. Yet for all their importance, population 3 stars themselves remain ghosts. No telescope has ever directly spotted one because they lived fast, died young, and faded into history before the first galaxies fully formed. The upcoming James Webb Space Telescope might change that. Its infrared eyes are perfectly tuned to hunt for their distant glow in the farthest reaches of space. If we find them, it would be like uncovering the universe's original blueprints, written in light older than time itself. What's truly humbling is realizing that every atom in your body heavier than hydrogen was once inside a star. But not just any star. Some of those elements might trace their lineage back to these primordial giants, the first ones to turn emptiness into chemistry, darkness into light. They were the universe learning how to build, and in their explosive deaths they gave us the materials to exist. Something out there is pulling entire galaxy clusters toward it, an invisible force so vast that it defies everything we know about the cosmic landscape. Astronomers call it the dark flow, and it's exactly as eerie as it sounds. Imagine dropping hundreds of marbles onto a stretched sheet, expecting them to roll randomly, only to watch them all slide toward one unseen edge. That's the puzzle we're facing. Thousands of galaxies moving in unison toward a point beyond the edge of our observable universe, as if tugged by a gravitational hand we can't see. This isn't just a subtle drift. Studies of galaxy clusters using the cosmic microwave background as a reference frame reveal velocities up to 1,000 kilometers per second, far faster than standard expansion models can explain. The kicker: this motion points toward a region of space with no known superclusters or mass concentrations powerful enough to cause it. It's like feeling a gust of wind in a sealed room. One radical explanation: the dark flow could be the gravitational fingerprint of a structure older than the Big Bang itself, perhaps a remnant of a prior universe or a neighboring bubble in the multiverse. Think of it as cosmic archaeology. Just as earthquake vibrations reveal hidden layers in Earth's crust, the motion of galaxy clusters might expose relics from before time began. Some theories even suggest these flows trace back to quantum entanglement between our universe and another, a ghostly connection forged in the first moments of creation. But skepticism abounds. Critics argue measurement errors or local voids might mimic the effect. Yet when independent teams using different methods like the Planck satellite and X-ray cluster surveys keep finding the same anomaly, it's harder to dismiss. Future missions like the European Space Agency's Euclid telescope could settle the debate, mapping galaxy motions with unprecedented precision. The implications are staggering. If the dark flow is real, it means our universe isn't just expanding, it's oriented, pulled toward something beyond the horizon of existence. Whatever lies out there, it's rewriting the rules of cosmology, forcing us to ask, was the Big Bang truly the beginning, or just one page in a much older story? Magnetism shouldn't have survived the Big Bang. In the universe's first moments, temperatures soared so high that even atoms couldn't form, let alone delicate magnetic fields. Yet somehow, faint traces of primordial magnetism linger between galaxies today, threads of force so subtle they're 100,000 times weaker than a refrigerator magnet. These ghostly fields shouldn't exist under standard cosmology, yet they've been detected threading through the cosmic voids, their presence etched into the polarized light of distant quasars. The mystery begins with inflation, that explosive expansion thought to have stretched the universe from quantum scales to cosmic proportions in less than a trillionth of a second. Most models assume any magnetic fields present before inflation would have been diluted into oblivion, stretched so thin their strength dropped to zero. But here's the twist: quantum fluctuations during inflation itself might have generated new magnetic fields. Picture the early universe as a stormy sea, with space-time itself rippling violently. Those tremors could have shaken charged particles into microscopic currents, imprinting weak magnetic fingerprints onto the fabric of space before matter even existed. These fields, though unimaginably faint, became cosmic scaffolding. As the first galaxies formed, their gravity amplified those primordial whispers, twisting and stretching magnetism into vast tendrils between clusters. Today, we see the evidence in the way charged particles spiral around these invisible lines, like iron filings revealing the shape of a magnet you can't see. The most compelling data comes from blazars, supermassive black holes firing jets of plasma across the universe. When their light passes through intergalactic space, its polarization twists in ways that betray the hidden magnetic fields it encountered along the way. The real shocker: these fields might have been midwives for the first stars. Without them, gas in the early universe would have collapsed into stars too slowly, leaving galaxies stunted. But magnetism adds just enough turbulence to stir the cosmic soup, helping matter clump faster while preventing runaway collapse. It's a delicate balance: too strong, and galaxies would have torn themselves apart; too weak, and stars might never have ignited at all. Critics argue these fields could be later contamination, seeded by supernova or active galaxies rather than relics from the Big Bang. But simulations show local sources can't explain their vast, uniform distribution. Upcoming telescopes like the Square Kilometre Array aim to map these fields in unprecedented detail, hunting for telltale patterns that would confirm their primordial origin. If they succeed, we'll have uncovered one of the universe's best-kept secrets: a force so fragile it shouldn't have lasted 14 billion years, yet quietly shaped everything we see. The Big Bang wasn't a beginning, it was a rebound. That's the mind-bending claim of loop quantum gravity, a theory that rewrites cosmic history by erasing the singularity entirely. Imagine the universe not as a fiery explosion from nothingness, but as a cosmic trampoline where space-time itself compresses to unimaginable density, then bounces back. In this framework, our universe didn't emerge from a point of infinite density. Instead, it's the aftermath of a prior cosmos that collapsed under its own gravity, reached a quantum limit, and sprang outward in what we now call the Big Bang. This Big Bounce scenario solves one of physics' most vexing problems: the singularity. Einstein's equations break down at the instant of the Big Bang, where density and temperature become infinite, a mathematical absurdity. But loop quantum gravity, which treats space-time as a woven fabric of tiny, indivisible loops, suggests a different fate. When the previous universe contracted to around 10 to the power of negative 99 cubic centimeters, these quantum threads couldn't tighten further. Space-time resisted, triggering a repulsive force so powerful it reversed collapse into expansion. Picture squeezing a spring to its limit. The harder you press, the more fiercely it pushes back. The evidence: subtle scars in the cosmic microwave background. Some physicists argue the CMB's temperature fluctuations aren't random but bear imprints of pre-bound structures like shadows of ancient galaxies cast onto the newborn universe. Even more provocative, if the bounce preserved certain quantum information, our universe might inherit mathematical constants or symmetries from its predecessor. Think of it as cosmic DNA, where the laws of physics get passed down through cycles of collapse and rebirth. Critics counter that without observable proof of the prior universe, the bounce remains elegant speculation. Yet experiments are underway. Gravitational wave detectors might someday catch echoes of pre-Big Bang events in the universe's oldest ripples. Others hunt for anomalies in large-scale galaxy distributions that could betray a recycled cosmos. What's truly staggering is the implication. Time might be endless, with universes rising and falling like breaths. Our Big Bang becomes just one heartbeat in an infinite cycle, each collapse purging the old universe's entropy, each rebirth resetting the cosmic clock. The singularity wasn't a wall, it was a doorway, and we're standing on the threshold of countless iterations before us. Deep in the cosmic voids, those vast, empty regions where galaxies are few and far between, there's a whisper of something that shouldn't be there. Astronomers call it the Great Annihilator, a ghostly echo of the universe's most violent showdown, matter and antimatter locked in a battle to the death. Every particle we know has an evil twin, a mirror version with opposite charge. When they meet, they annihilate in a flash of pure energy. The Big Bang should have created equal amounts of both, leaving nothing behind but light. Yet here we are, in a universe drowning in matter. So where did all the antimatter go? The answer might be hiding in the darkest, emptiest corners of space. Gamma-ray telescopes have spotted something bizarre: faint, diffuse glows in regions where there's almost no matter at all. These aren't the brilliant bursts of collapsing stars or the fiery jets of black holes. They're slow, lingering emissions, like the afterglow of a firework that faded billions of years ago. The leading theory: these are the last remnants of antimatter pockets, isolated survivors from the early universe that took far longer to die. Imagine two armies clashing in the dark, matter and antimatter, annihilating at their borders over eons, leaving behind only gamma-ray smoke signals. But here's the twist: these signals aren't where we'd expect them. If antimatter had been evenly mixed with matter, the entire universe would have been wiped clean in seconds. Instead, the gamma rays cluster in specific voids, suggesting antimatter wasn't just rare. It was clumpy, trapped in cosmic prisons while matter escaped to build galaxies. Some physicists speculate these pockets were protected by freak quantum conditions, regions where antimatter dominated just long enough to leave a trace. Others think they're evidence of something even stranger: primordial black holes evaporating, their deaths releasing stored antimatter like a time capsule from the first moments of creation. The hunt now turns to next-generation telescopes like the Cherenkov Telescope Array, which could map these gamma-ray ghosts with unprecedented precision. If they find patterns matching antimatter decay, it would be like uncovering the charred remains of the universe's first war, a conflict where matter somehow cheated death. The Great Annihilator isn't just a curiosity, it's a clue to why anything exists at all. And buried in those silent voids, the universe might still be holding onto its oldest secret: how we got lucky enough to be here. We take for granted that space is flat, an endless sheet stretching in all directions. But what if the universe isn't just stretching but also curving in ways we can't see, like an invisible maze with no exit? The shape of the cosmos isn't just geometry, it's a window into its birth, and the latest data suggests reality might be far stranger than a simple infinite plane. Start with the cosmic microwave background, that ancient light from the universe's toddler years. If space were perfectly flat, temperature variations in the CMB should follow predictable, random patterns. But they don't. Certain fluctuations appear eerily aligned or repeat at specific scales, like echoes in a hall of mirrors. One explanation: the universe could be finite but wrapped. Imagine a video game where crossing the right edge teleports you to the left. On a cosmic scale, this could mean light has been looping around a closed universe for billions of years, creating duplicate patterns in the CMB. Then there's the donut theory, a shape mathematicians call a 3 torus. Picture our universe as a giant donut, where traveling far enough in one direction brings you back to where you started. This isn't just a funhouse illusion. It would explain why some large-scale structures in the cosmos seem to reappear in distant, unrelated regions. Surveys mapping millions of galaxies have flagged odd repetitions, clusters of quasars or supervoids that look suspiciously similar, as if the universe ran out of unique blueprints and started recycling. But here's the catch: if space is curved, why don't we see obvious distortions? A spherical universe, for instance, would bend light like a funhouse mirror, making distant galaxies appear warped. Yet most observations align with flatness. The answer might lie in scale. The universe's curvature could be so subtle that it's only detectable across distances larger than the observable cosmos, like an ant on a beach ball mistaking its surface for a flat plane. Alternatively, cosmic inflation might have stretched any early curvature to near flatness, leaving only faint traces in the CMB's geometry. The stakes are higher than they seem. A closed universe would eventually collapse in a big crunch, while an open or flat one would expand forever. A donut-shaped cosmos, though, would rewrite the rules of topology itself, implying hidden connections between seemingly separate points in space. Future missions like the European Space Agency's Euclid telescope aim to measure the universe's shape with precision by tracking how gravity distorts galaxies across billions of light-years. If they find even a hint of curvature, it would upend our understanding of everything from dark energy to the Big Bang's true nature. So is the universe flat, a glazed donut, or something even weirder? For now, the data leans toward flat, but the anomalies keep piling up, whispering that reality might be playing tricks on us. Until we crack the code, the cosmos remains the ultimate escape room, with clues hidden in the oldest light we can see. Black holes don't just swallow matter, they devour information itself, erasing the very history of everything that falls in. This cosmic amnesia, known as the Information Paradox, has haunted physicists since Hawking first showed black holes must evaporate, taking their secrets with them. But twist the lens just right, and you'll see this isn't just a black hole problem. It's a mirror of the Big Bang's deepest mystery: how a universe can emerge from nothingness without losing its own origin story. The key lies in a radical idea called the AD/CFT correspondence, a theoretical bridge connecting gravity to quantum mechanics. Picture the universe as a hologram, where everything happening inside a volume of space particles colliding, stars forming, is encoded on its boundary. Black holes stretch this concept to the extreme. According to AD/CFT, the information they seem to destroy isn't lost. It's scrambled into quantum noise on their event horizons, like a cosmic hard drive written in unreadable code. Now rewind to the Big Bang. If the singularity behaved like a black hole in reverse, spewing out matter instead of consuming it, the same holographic rules might apply. The universe's initial conditions, its very blueprints, could be etched onto some primordial boundary we can't yet see. Here's where it gets mind-bending. The same math that resolves the black hole paradox might explain why the Big Bang didn't spawn a chaotic, lawless cosmos. Just as a black hole's surface holds a perfect record of its contents, the Big Bang's boundary could have encoded the seeds of structure we see today: galaxies, voids, even the cosmic microwave background's faint wrinkles. In this view, the Big Bang wasn't a true singularity but a transformation, a moment when information flipped from one dimension to another. Critics argue this is speculative, that without experimental proof, it's just elegant guesswork. But the stakes are universe-sized. If AD/CFT is right, the paradoxes plaguing black holes and the Big Bang aren't flaws, they're clues, hints that reality is far more interconnected than we dreamed. Future gravitational wave detectors might spot anomalies in black hole mergers that reveal this hidden coding, while quantum simulators could recreate holographic principles in the lab. The haunting beauty of this idea, it suggests that nothing, not even the birth or death of a universe, truly vanishes. Information persists, woven into the fabric of space itself, waiting for us to learn its language. And if we do, we might finally read the universe's first message to itself, written in the fire of creation. Imagine a galaxy so faint it barely glows, a wispy collection of stars floating like dust in the void. Yet when scientists weighed it, they found something impossible. This cosmic ghost, known as Dragonfly 44, has the mass of the entire Milky Way, yet emits less than 1% of the light. The reason: 99.99% of it is pure dark matter, an invisible scaffold holding stars together like flies caught in a spiderweb of shadows. This isn't just a bizarre outlier, it's a cosmic crisis. According to standard models of galaxy formation, structures like Dragonfly 44 shouldn't exist. Here's why. In the early universe, dark matter clumped first, forming gravitational wells where gas pooled, cooled, and eventually ignited into stars. But for a galaxy to be this dominated by dark matter, those star-forming processes had to nearly fail, like a car engine turning over but never fully starting. The handful of visible stars in Dragonfly 44 are mere accidents, flickering candles in a cathedral built for something unseen, the real shocker. Dragonfly 44 isn't alone. Telescopes have since uncovered dozens of these ultra-diffuse galaxies, each eerily dim yet brimming with hidden mass. Some, like NGC 1052DF2, are even more extreme, with so few stars that they're effectively transparent. If you flew through one, you might not realize you were in a galaxy at all, until the unseen gravity twisted your ship's course. So where did these phantoms come from? One theory points to failed galaxies that lost their gas early, strangled by the heat of nearby galaxy clusters before stars could form en masse. Another suggests their tidal debris shredded remnants of larger galaxies torn apart by collisions, leaving behind only their dark matter skeletons. But the most unsettling idea: these might be pristine relics of the early universe, pockets where dark matter never quite sparked the fireworks of star birth. They could be cosmic fossils, frozen in time from an era when the universe was too young and too cold to light up properly. The implications ripple far beyond a few oddball galaxies. If dark matter can clump this densely without triggering star formation, our entire understanding of structure formation might need rewiring. Maybe dark matter interacts with itself in ways we've never detected, or perhaps ordinary matter behaved differently under the extreme conditions of the early cosmos. Future telescopes like the Vera Rubin Observatory aim to find thousands more of these phantoms, mapping their distribution for clues. For now, Dragonfly 44 remains a riddle wrapped in an enigma. It's a galaxy that shouldn't be, a cosmic contradiction that whispers we've barely scratched the surface of dark matter's secrets. And if we're wrong about how galaxies form, what else might we have missed in the shadows? Buried in the faint hum of the cosmos could be the oldest echoes of all ripples in space-time, so ancient they predate atoms, light, even the very concept of time as we know it. These aren't just any gravitational waves, they're quantum gravity fossils, primordial tremors from the universe's first infinitesimal fraction of a second. If detected, they'd be our first direct glimpse into the era when gravity itself was still figuring out how to behave. The story starts with inflation, that explosive expansion thought to have stretched the universe from quantum scales to cosmic proportions in less than a trillionth of a second. During this frenzy, quantum fluctuations, tiny jitters in the fabric of reality got magnified to cosmic proportions. Some became the seeds of galaxies, but others did something far stranger. They warped space-time itself, creating gravitational waves with wavelengths as vast as the observable universe. These waves never stopped ringing. They've been propagating for 13.8 billion years, carrying a message from the instant when gravity and quantum mechanics were still dancing together. The kicker, these waves aren't just relics, they're Rosetta Stones for physics. Einstein's theory of general relativity breaks down at the energies present during inflation, where quantum effects dominate gravity. By studying the pattern of these primordial ripples, we could uncover how gravity behaves at scales a trillion times smaller than an atom. It's like finding a recording of the universe's first cry, a soundbite from the moment physics was born. Hunting them isn't easy. Today, these waves would be astonishingly faint, with frequencies too low for current detectors like LIGO to catch. But there's a workaround, their imprint on the cosmic microwave background. As these gravitational waves propagated through the early universe, they subtly twisted the polarization of light in the CMB, leaving behind a distinct swirling pattern known as B modes. Spotting this signature would be like finding dinosaur footprints fossilized in rock, except the dinosaur is the universe's infancy, and the rock is the oldest light we can see. The search has already seen false starts. In 2014, the BICEP2 team announced they detected B modes, only to realize the signal was mostly interstellar dust. But next-generation projects like the Simons Observatory and CMB Stage 4 are poised to try again with instruments 10 times more sensitive. If they succeed, the implications would rewrite textbooks. The strength of these waves could reveal whether inflation was driven by a single quantum field or a cascade of them, like layers in an onion. Their spectrum might even hint at extra dimensions, subtle vibrations from hidden folds in space-time. Skeptics argue the signal could be drowned out by foreground noise forever, leaving us with only theoretical guesses. But if we do catch these whispers, it would bridge the last great divide in physics, merging quantum mechanics and gravity into a single framework. Suddenly, the universe's first moment wouldn't be a black box of infinities. It would be a laboratory, its data etched into the sky, and the most humbling thought. These ripples have been passing through your body every second of your life, unnoticed. The universe's oldest song is still playing, we're just learning how to hear it. Our universe won't just fade, it'll dissolve into a sea of quantum static so vast that even time loses meaning. Picture a clock ticking not for billions or trillions of years, but for 10 to the power of 10 to the power of 56 years. That's a 1 followed by more zeros than there are atoms in the observable universe. This is the timescale where physics as we know it breaks down, where the very concepts of structure and energy become relics of a forgotten age. It starts with heat death, the slow but inevitable victory of entropy. Over the next 100 trillion years, the last stars will gutter out, leaving behind cold husks of white dwarfs and neutron stars. Even these remnants won't last. Quantum tunneling ensures that given enough time, around 10 to the power of 32 years, every solid object in the cosmos will spontaneously decay into iron dust. Black holes, the universe's final survivors, will dominate the landscape for eons, feasting on stray particles until they too evaporate via Hawking radiation. The last stellar mass black hole will vanish around 10 to the power of 67 years from now, leaving behind only photons and the faintest whispers of subatomic particles drifting through absolute zero. But the story doesn't end there. Over incomprehensible spans, even the vacuum of space itself becomes unstable. Quantum fluctuations could trigger vacuum decay, a ripple in the fabric of reality that rewrites the laws of physics at light speed. One random hiccup in an empty void might spawn a new Big Bang, erasing our universe's history in an instant. Alternatively, if dark energy behaves unpredictably, it might tear apart the quantum fields that give particles mass, reducing all matter to a featureless soup. Yet the most haunting possibility is proton decay. If protons, the bedrock of atoms, aren't truly stable, they'll eventually disintegrate into positrons and gamma rays. Current experiments suggest this takes at least 10 to the power of 34 years, but given infinite time, every proton in the cosmos will blink out of existence. The universe becomes a thin gruel of radiation and black hole remnants expanding into eternal darkness. In the far, far future, time itself may cease to have meaning. Without events to mark its passage, without structures to change, the universe enters a state of heat-death equilibrium, not an explosion or an implosion, but a whisper fading into silence. Some theories suggest quantum tunneling could still spawn Boltzmann brains, fleeting consciousnesses hallucinating existence in the void, but even these phantoms would vanish. The chilling takeaway: every galaxy, every planet, every thought ever had is destined to erase itself from the cosmic ledger. But here's the twist: in a multiverse or cyclic cosmology, our universe's death might be just one note in an endless symphony of creation and destruction. The atoms in your body could one day fuel a new Big Bang, your existence recycled into another reality's dawn. The ultimate fate of the universe isn't an end, it's a question mark written in the ashes of time. From quasars older than time itself to phantom antimatter universes hiding in the void, the universe's origin story is stranger than fiction. We've uncovered black holes that could be dark matter in disguise, galaxies made almost entirely of shadow, and whispers of reality being nothing more than a cosmic hologram. And yet, here's the unsettling truth: we've barely scratched the surface. For every mystery solved, a dozen more emerge, each rewriting the rules of physics as we know them. Think about it: we're standing at the edge of human understanding, peering into the abyss where even the laws of nature seem to break down. The universe doesn't owe us answers. It doesn't play by our expectations, and that's what makes this journey so exhilarating. Every forgotten fact we've explored today, from primordial black holes to the dark flow dragging galaxies toward something unseen, is a reminder that the cosmos is still writing its own biography, with chapters we haven't even imagined yet. So here's the real question: which revelation shook you to your core? Was it the Boltzmann brain paradox making you doubt reality itself, or the specter of phantom energy tearing space-time apart atom by atom? Maybe it was the ancient helium hydride molecule chemistry's first building block, waiting billions of years to be found. Whatever it is, the conversation doesn't end here. The universe is a puzzle with pieces still missing, and you're part of the search. Drop your mind-blowing moment in the comments, and if you're hungry for more cosmic mysteries lurking beyond the textbook answers, hit subscribe. The next discovery might be the one that rewrites everything. Don't let it unfold without